Okay, let's unpack this. You've dropped a stack of sources on our desk, all pointing towards one incredible thing: how modern computers manage to stay incredibly fast and incredibly reliable, often at the exact same time.
Right, because when we talk about the raw horsepower in today's machines, the screaming fast GPUs rendering complex worlds, those NVMe SSDs loading games in a blink.
Or AI accelerators chewing through data.
Exactly. They aren't just sitting there in isolation. They need to talk.
They have to talk to the CPU and to each other, and they have to do it fast. And the superhighway connecting all those critical components is, well, overwhelmingly PCI Express or PCIe.
Precisely. And the speed demands on this highway are just escalating wildly. Your sources track this relentless race from 16 gigatransfers per second GTs per lane in PCI Poo 4.0.
Doubling to 32 DTs in 5.0.
Then again to 64 GPs in 6.0, and now PCIe 7.0 is aiming for a staggering 128 GTs per lane. Just massive numbers.
Doubling speed sounds simple, right?
Yep.
Just turn up the dial. But trying to cram data that fast down physical wires, circuit board traces, the signal itself starts to break down. Errors pop up.
Yeah, it's not just turning up the volume.
It's like trying to understand someone shouting perfectly clearly, but in a hurricane across a football field. It just doesn't work the same.
That's a good analogy. The physical channel, it just fundamentally fights back harder the faster you go. Signals lose strength. That's insertion loss or attenuation.
Right.
The timing gets wobbly. That's jitter. Signals on one wire interfere with neighbors.
Crosstalk.
And of course, there's always random noise just floating around.
And all that noise and wobbly timing means the clear difference between a digital 0 and 1 gets blurred. Engineers talk about the eye of the signal shrinking. So the receiver chip has a much harder time deciding, yep, that was definitely a 1, leading to more raw errors coming off the wire.
Precisely. And while engineers are wizards at making better cables using advanced materials, there are practical limits, economic limits, physical limits. You can't make the raw signal perfectly clean just through hardware anymore, not at these speeds.
So you absolutely have to have a plan for dealing with the errors you can't eliminate. And that's where this deep dive based on your sources comes in. We're zeroing in on how PCIe maintains its rock-solid reliability despite these speed challenges.
And we're focusing on a fundamental technique that became, well, absolutely essential in recent generations: forward error correction, or FEC.
Think of this as your shortcut, really, to understanding the sophisticated digital safety net under those hyperspeed connections.
Let's maybe set the stage by looking at the high-speed challenge in a bit more detail, because it really explains the why FEC became necessary.
Okay.
So PCI's core architecture is these point-to-point links. Think of like a dedicated connection between the CPU and the GPU.
Right, one-to-one.
And each connection is made up of one or more lanes. These lanes are full duplex pairs of differential signals, basically 2 wires per direction, sending opposite signals. That helps reject noise, which is good.
And the speed race, as we said, is just relentless. Those GTs numbers 16, 32, 64, 128. What's fascinating here, and the sources point this out, is the jump from PCIe 5.0 at 32 GTs to 6.0 at 64 GTs. They managed to double the speed without doubling the fundamental frequency on the wire. That seems key.
It is key. PCIe 5.0 signaling pushed the channel to a frequency limit around 16 gigahertz, sometimes called the Nyquist frequency. It's related to how fast you can sample.
Okay.
Pushing to 64 GTs using the old method would have meant doubling that frequency, trying to push signals at like 32 gigahertz through copper traces. That gets exponentially harder.
Right, the physics just fights back even harder.
Absolutely. Higher frequencies just exacerbate all the signal integrity problems we mentioned. Insertion loss gets way worse. Jitter becomes a bigger percentage of the timing window, which is already shrinking. Crosstalk is more problematic. Noise is a constant battle.
It's like trying to listen to faint whispers in a room that's suddenly gotten incredibly noisy. Your chances of misunderstanding just skyrocket.
And that shrinks the signal I, leading directly to a higher raw bit error rate, the BER. It becomes practically impossible, or at least prohibitively expensive, to engineer the physical channel alone to keep that pristine signal quality needed at these speeds using the older methods.
Okay, so the core problem statement laid out in the sources is higher speeds inevitably introduce more signal problems. And this escalating challenge required a fundamental shift in error handling strategy.
Right. It pushed PCIe towards different signaling, we'll get to PAM4, and critically towards proactive error correction, FEC.
But before this shift,
in
earlier PCIe generations, say up through 5.x, The strategy was completely different, wasn't it?
Totally different philosophy. Back then it was engineer the physical layer to be almost perfect,
Huh.
make the raw signal incredibly clean, and if a rare error does sneak through.
Just detect it and ask for a do-over.
Exactly. The classic detect and retry.
How did they detect those errors so reliably?
The workhorse was the cyclic redundancy check, or CRC. These are, well, incredibly powerful mathematical tools. You generate a short check value for a block of data.
Okay.
The receiver recalculates the CRC if it doesn't match the 1 cent. With extremely high probability that errors happened. And they had CRCs at multiple layers, the data link layer, the transaction layer, very robust detection.
But a CRC just flags an error, right? It doesn't tell you where it was or how to fix it.
Correct. So if a CRC failed, the recovery mechanism kicked in, link layer retry, or LLR. The receiver basically sends back a message, an NA, negative acknowledgement, saying that packet was bad, send it again. The transmitter keeps a copy in a buffer until it gets the all clear.
And LLR has been fundamental to PCIe since, version 1.0, right?
It's the ultimate guarantor of data correctness. Now, the reason this whole detect and retry thing worked up through PCIe 5.x is because the target for the raw bit error rate on the physical channel was incredibly stringent, like 10 to the power of -12.
Hold on. 10 to the -12. That's 1 error per trillion bits transmitted. That sounds impossibly clean just from the wire itself. How did they manage that?
Well, they relied heavily on sophisticated digital signal processing techniques, equalization,
EQ.
complex algorithms running on the chips at both ends, transmitter and receiver, TXEQ, RXEQ, using methods like CTLE, DFE. These compensate for the predictable ways the signal degrades, boosting certain frequencies, canceling echoes, that kind of thing.
Cleaning up the signal after the fact, digitally.
Pretty much. And I saw something about pre-coding being introduced in PCIe 5.0. What was that about?
Yes, good point. Even with NRZ at 32 GTs, that clean channel started seeing some new challenges, particularly with burst errors, where several bits in a row get corrupted. One type of equalization, DFE, could sometimes actually propagate an error, turn a single bit flip into a short burst. So pre-coding was added in 5.0 specifically to help break up those potential burst errors, make them look more like isolated single errors again.
Which the existing system was better at handling. Exactly. It was a sign, really, that error characteristics were becoming a concern even at 32 GTs with the old NRZ signaling.
Okay, so the philosophy up to 5.x was make the channel incredibly clean, 1012 BER, using NRZ and lots of EQ, use CRCs to find the very rare errors that slip through, and LLR to fix them by resending.
That's the summary. FEC wasn't seen as necessary because the raw error rate was already so low. And adding FEC, well, it would have just added unwanted latency.
And latency is bad for PCIe.
Latency is poison for a load store interconnect like PCIe, which sets the stage perfectly for the turning point, the big shift in PCIe 6.0. This is where PM4 comes in.
And makes FEC absolutely non-negotiable.
Exactly. The goal for 64 GTs was to double the speed without doubling that fundamental Nyquist frequency, remember? Keeping it around 16 gigahertz like PCI 5.0.
Right.
The only practical way to do that on copper was to switch signaling from NRZ,
non-return to 0, 1 bit per symbol, 2 voltage levels.
PM4, pulse amplitude modulation with 4 levels.
4 voltage levels.
Right. With 4 levels, you can encode 2 bits per symbol, so you're transmitting twice as much data in the same amount of time, using the same fundamental channel bandwidth. That's the magic.
But the sources really hammer home the trade-off with PM4. It's not free.
It's a massive trade-off, those 4 levels. They have to fit into roughly the same total voltage swing that NRZ used for just 2 levels.
So the space between each level gets cut way down.
Dramatically. The vertical separation, the signal eye height, shrinks significantly compared to NRZ.
The steps are much closer together, like trying to read finer print.
Precisely, and that makes the signal much more sensitive to noise, to jitter, to any remaining interference. It's like trying to distinguish 4 subtly different shades of gray in dim, flickering light instead of just black and white.
Okay, and the direct consequence of that sensitivity, what happened to that beautiful 10 to the -12 raw BER?
It's fundamentally changed. For PCIe 6.0 using PM4, the design target is a first bit error rate, or FBER, of 10 to the power of a -6.
10 to the -6. Whoa. Let that sink in. That's 1 initial error event per million bits, compared to 1 error per trillion bits before. That is, wow, 6 orders of magnitude worse raw channel quality coming off the wire.
It's a drastic difference, and this is the critical point. If your raw error rate is 10 to the -6, you cannot rely solely on detect and retry. on LLR.
Why not?
Because retries would be happening constantly.
Oh, yeah.
Roughly one retry attempt for every million bits or every megabit of data transferred.
Your link would just grind to a halt, spending all its time resending data, not getting new work done. Performance would collapse. Latency would be awful.
Exactly. So PM4 enabled the speed increase at a feasible frequency, but it created this intrinsically noisier channel. This made forward error correction, proactively correcting errors as they arrive, not just a nice-to-have, but an absolute requirement.
You had to clean up that 10.6 rate before it hit the layers that rely on retries.
Precisely. To get the effective error rate way, way down so that LLRs only needed very, very rarely. It was a fundamental philosophical shift. Accept the noisy channel and fix it in digital processing rather than trying to make the analog channel perfect.
Okay, so FEC became essential. Let's dive into what it actually is and how PCIe implements it. We said it adds redundancy, allows the receiver to correct errors without asking for a retransmission.
Yeah, think of it with those analogies your sources mentioned, like adding extra clues to your message. Even if some parts get garbled, the redundancy, the extra bits, provide enough context for the receiver to figure out the original content correctly.
Or the simpler idea of sending each piece of info multiple times and doing a majority vote if one copy gets flipped.
Right. While PCI's FEC is obviously more complex math, the core concept is adding carefully designed redundancy, these parity bits, to the data.
Which forms a code word.
Right, a code word. And errors within that code word can then be identified and corrected at the receiver using those extra parity bits.
And in PPIe 6.0's case, the correction happens at the symbol level you mentioned, since PM4 sends symbols.
Yes, the FEC is designed specifically to fix errors affecting single multi-bit symbols within its processing block.
Now, the sources really emphasize that the PCIe 6.0 FEC mechanism had to be lightweight and have extremely low latency. Why was that so critical again for PCIe?
It goes right back to PCIe's role as that load-store interconnect. How the CPU talks directly to memory, GPU, storage. Latency is absolutely king.
Every nanosecond counts.
Every nanosecond you add processing data on the fly translates directly into slower application performance, higher CPU idle time waiting for data. It's just bad.
So unlike maybe a network link like Ethernet, where you might tolerate hundreds of nanoseconds, maybe even microseconds, for stronger error correction, PCIe needs something much faster.
Oh, way faster. The target stated in the sources for the total time to do the FEC decoding plus the subsequent CRC check is less than 2 nanoseconds, sub 2 sets.
Wow, that is incredibly aggressive.
It is. And that tight latency target fundamentally drives the FEC design choices.
How so?
It dictates that you simply can't use a massively powerful, complex FEC code that needs a lot of computation time or deep interleaving. The philosophy becomes, use a very fast, relatively simple FEC that can correct the most common types of errors you expect from PM4.
Like those single symbol errors.
Exactly. And then rely on the existing, already fast LLR mechanism for the very rare cases where the FEC gets overwhelmed or misses something.
So you avoid penalizing every single packet with the delay of a complex, slow decode. You optimize for the common case.
That's the strategy. It's better to have a fast FEC handle most errors and have a rare, slow LLR event than to make every packet slow.
What were the key operational targets they designed around for this system then, the numbers?
Okay, so they aimed for that raw PM4 channel FBER to be around 10.6. The FEC plus CRC processing needed to be under that 2 ends mark.
Right.
The combination of FEC correcting errors and CRC catching the rest needed to reduce the probability of a fixed size packet. A flat D, we'll get to that needing an LLR retry down to about 10.6.
So make the retry event itself rare.
Very rare. And they knew the LLR round trip itself, when it did happen, would take maybe around 100 ends, much slower than the normal path.
So the goal is crystal clear. Make that slow 100 ends retry event incredibly infrequent, like 1 in a million packets, by having the super fast sub 2 ends FEC handle the vast majority of the errors from that 10.6 raw rate.
Exactly. It's a carefully engineered probability game. And the specific FEC code chosen reflects this. It's described as 3-way interleaved single symbol, correct FEC.
Okay, let's break that down. Single symbol correct. We got that fixes 1 symbol error per block. What about interleaved and 3-way interleaved?
Interleaving is a crucial technique, especially for handling burst areas.
Ah, right. We mentioned noise spikes, or that DFE error propagation could corrupt several consecutive bits or symbols on the wire.
Exactly. A simple FEC code might only be able to fix, say, 1 error in its block. If a burst puts 3 errors right next to each other within that one block, the FEC fails.
So interleaving spreads those burst errors out. How does that work?
Precisely. Before you send the data, you take symbols from multiple different correction blocks and you shuffle them up, interleave them for transmission. Think of dealing cards from 3 different decks into one sequence.
Okay.
At the receiver, you de-interleave them. You put them back into their original blocks, their original decks. Now that burst error that hit 3 symbols contiguously on the wire might, after de-interleaving, result in only 1 error landing in block A, 1 error in block B, and 1 error in block C.
Aha. So the burst on the wire gets broken up across multiple FEC blocks at the receiver. And if each block now only has 1 error,
the single symbol correcting FEC in each block can handle it. It turns an uncorrectable burst into multiple correctable single errors.
that's really clever. Like dealing cards, like you said, if you drop a section of the combined stack, you lose cards, but they were destined for different hands anyway, so each hand maybe only loses 1 or 2 cards, not its whole winning set.
Perfect analogy. And 3-way interleaved just means they specifically designed it to spread data across 3 logical correction domains, or streams. This particular depth 3 ways was likely chosen as a good balance. It effectively handles the kinds of burst errors expected with PAM4 while keeping the interleaving relatively shallow, which helps meet that super tight sub-10s latency target. Deeper interleaving would add more delay.
Makes sense. And the sources had an example showing how a burst hitting symbols B3, C3, A4 in the transmitted sequence would end up as single errors in blocks B, C, and A after de-interleaving.
Exactly, making them correctable.
Yeah, that interleaving is key. And this whole FEC process, working on fixed size correction blocks, that naturally led to another big change in PCI 6.0, FLITs. Why were FLITs necessary?
Because most FEC codes, especially efficient hardware implementations, work best on fixed-size chunks of data, those code words we mentioned. The older PCI generations transmitted variable-size packets, like transaction layer packets, TLPs. They could be quite short or quite long. Trying to wrap a fixed block FEC efficiently around those variable packets, it would be complex, probably inefficient, add overhead.
So they just standardized the container size for transmission.
Exactly. In PCIe 6.0 and later, especially when running at these high PM4 FEC speeds, all data is packaged into fixed 256-byte units. These are called flow control units, or FLAITs.
256 bytes. What's inside one of these FLAITs? How is it broken down?
The sources detail it nicely. You get 242 bytes for the payload. That's where your actual data goes, park of TLPs, other control messages.
Okay, 242 payload.
Then you have 8 bytes for a robust CRC check value. That covers the payload.
8-byte CRC. Got it.
And finally, 6 bytes of FEC parity data, the redundancy bits.
So 242 plus 8 plus 6 was 256 bytes total.
Okay.
And those 6 FEC bytes, they actually protect both the 242 bytes of payload and the 8 bytes of CRC.
That's correct. The FEC parity is calculated over the preceding 250 bytes, payload plus CRC. So even the CRC itself is protected against errors by the FEC before it gets checked. It's all part of the code word.
Huh. Did switching to fixed-size FLAITs offer any other benefits beyond just making FEC easier to implement?
Yeah, a couple of important ones are mentioned. It eliminates the need for the older 128B130B encoding scheme that previous gens used. That had about 1.5% overhead, just for ensuring enough signal transitions. FLIT mode gets that efficiency back.
Nice.
It also standardizes link layer packet handling and buffer sizes. Having fixed 256-byte units can simplify the design of the PCIe controller logic, potentially saving power or area. So FEC was the main driver, but there were definitely some nice side benefits too.
All right, so we've got the messy PM4 signal, the lightweight, low-latency, interleaved FEC designed to handle most of the mess, and the fixed FLIT packaging to make it all work smoothly. Now let's put it all together. How do FEC, the CRC, and the classic LOR mechanism work as a team in PCI 6.0 and 7.0 to deliver that required reliability?
This is really the crucial part, the layered defense. It's not just one thing, it's how they operate in sequence, one after the other.
Okay, walk us through it. A 256-byte FLIT arrives at the receiver off the wire. First step.
First, the receiver's hardware immediately processes that FLIT through the FEC decoding logic. It uses those 6 parity bytes to try and find and fix errors in the 250-byte block, payload plus CRC. This is the fast first pass, designed to catch and correct those anticipated single-symbol errors, fixing problems from the noisy channel right away.
So it attempts to fix errors on the fly before anything else really happens to the data.
Exactly. Then, step 2. After the FEC has done its best and potentially corrected some bits in the payload or maybe even in the CRC field itself, the receiver performs the CRC check.
It calculates a new CRC value over the 242 bytes of payload as they exist after potential FEC correction.
Precisely. And it compares that newly calculated CRC to the 8 bytes of CRC data that came in the FECRT, which again might also have been corrected by FEC.
And the CRC comparison is the robust detection step. It verifies if the data is clean after FEC.
Yes. Even if the lightweight FEC couldn't fix everything, or maybe missed an error, the 8-byte CRC is incredibly powerful at detecting that residual error. The probability of a CRC failing to detect an error, what they call aliasing, is vanishingly small. Extremely low FIT rates, as the sources say.
Okay, so FEC tries to fix CRC double checks. What if the CRCs don't match after all that?
That's the signal that errors remain, which the FEC couldn't handle. And this is where the third layer, the safety net, link layer retry LLR, kicks in.
Ah, the old reliable.
The receiver discards the bad FEC. It doesn't pass corrupted data up the stack. It sends a NEC message back up the link to the transmitter.
Saying, send that FEC again.
Exactly, triggering the transmitter to resend that specific FET from its buffer.
The rules are really clear then. FEC handles the bulk of the expected PM4 errors and does it super fast. CRC acts as the near-perfect detector to catch almost anything the lightweight FEC might miss. And LLR is the final backstop, ensuring ultimate data correctness by getting a clean copy. But importantly, only when absolutely necessary.
That's the synergy. That's the whole point. The entire system is tuned so that an event requiring that relatively slower LLR is very rare, targeting that 10 to the minus 6 probability per FLIT we talked about.
Right. One bad FLIT per million, roughly.
This layered design allows PCIe to embrace the inherently noisier PM4 signaling needed for speed while still delivering the rock-solid reliability users expect and maintaining high performance because retries aren't constantly bogging things down.
It's a really elegant solution, actually, accepting a certain amount of mess at the physical layer and then building layers of digital intelligence on top to systematically clean it up.
It is, and it really highlights a common theme in high-speed digital design today, you know? You push the physics, you accept some noise, you fix it digitally.
Speaking of design, there were obviously some tough engineering trade-offs made here to achieve this balance. You mentioned latency already. You can't have maximum speed, minimum latency, zero overhead, and perfect reliability all at once, right?
Absolutely not. There are always compromises. The primary constraint, as we discussed, driving many choices, was that latency target, that sub-2 nanosecond goal for FEC plus CRC,
Right.
that forced them towards a lightweight FEC code. It's fast, but it limits its correction power compared to heavier codes you might see in, say, long-haul communications or storage systems where latency is less critical. So some errors will get through the FEC. That's an accepted part of the design.
So the big compromise there was basically correction strength versus processing speed.
Precisely. Speed, low latency for every packet processing was prioritized.
What about bandwidth overhead? Adding 14 bytes of error coding, 8 for CRC plus 6 for FEC, to every 242 bytes of payload and a FLAT. That sounds like it could add up.
Well, yeah, the FLIT level itself, that's roughly 5.8% overhead just for the error coding bytes, which isn't trivial.
Okay.
However, remember that FLIT mode also eliminated the older 128B, 130B encoding overhead, which was about 1.5%.
Right.
And FLITs can offer other efficiencies too, perhaps packing small packets better sometimes. So the sources suggest the net impact on overall payload bandwidth efficiency compared to previous generations is actually aimed to be less than 2%. It's still a trade-off. You are sending more raw bits for the coding, but the overall impact is minimized.
Okay, less than 2% net isn't too bad then. What about power and silicon area? More complex logic always costs something there.
It does, absolutely. The FEC logic, the interleaving logic, plus the complexity of the PM4 transceivers themselves, it all adds power consumption and requires silicon area on the chip.
Makes sense.
However, again, the lightweight nature of the chosen FEC helps keep that incremental cost lower than a more complex, power-hungry code would. And other PCIe 6.0 features, like the L0P power state, help manage overall link power by allowing parts of the link to enter lower power states when they aren't fully utilized. Plus, as we said, standardized FLAT sizes might simplify some buffer management logic, potentially saving some area elsewhere. It's all interconnected.
So it really was a very delicate balancing act, wasn't it? Finding an FEC that was good enough to enable PM4 and meet that low retry probability target. But not so complex or powerful that it added unacceptable latency, ate too much bandwidth, or consumed excessive power or silicon area.
That's exactly right. It's a highly optimized solution tailored specifically for the unique requirements and constraints of the PCI interconnect. And this balancing act, well, it continues as we look ahead.
Because PCI 7.0 is pushing the speed even further, doubling again to 128 GTs per lane. Does it stick with the same fundamental architecture, PM4 FLITs, FEC?
Yes, the sources are clear on that. PCIe 7.0 builds directly on the foundation established in 6.0. It uses PM4 signaling, it uses FLITs, and it employs a similar layered error management strategy involving FEC, CRC, and LLR. The core architecture seems scalable, at least for this next speed jump.
What gets harder then, going from 64 to 128 GTs? Where's the main challenge?
Signal integrity. Just
Yeah.
maintaining a usable signal at that speed over copper traces and through connectors becomes an even bigger challenge. You need even more sophisticated equalization techniques, even tighter control over jitter from all sources, better noise mitigation. Everything gets harder.
So the FEC system, even if it's fundamentally similar, has to perform effectively in an even more stressed, noisier channel environment?
Exactly. The margins get tighter everywhere.
Did the sources mention any early signs of how 7.0 is actually looking in practice? Any demos or data?
There was an interesting note about a recent PCIe 7.0 demonstration. I think it showed a raw BER of 10 to the power of -10 achieved over a cable link.
Wait, 10 to the minus 10? That's way better than the 10 to the minus 6 FBER design target they used for PCIe 6.0's FEC, right?
It is significantly better, 2 orders of magnitude better raw channel quality than the worst case they designed the 6.0 FEC system to handle.
Wow. That sounds like it could provide a lot of margin then. Does that mean maybe FEC isn't quite as critical for 7.0 if the raw channel can be that good?
Well, it certainly provides margin, yes. If that kind of 10-10 performance can be achieved reliably and cost-effectively across the wide range of real-world channels, motherboards, cards, and components out there, remember that was likely a demo under controlled conditions.
Good point. System designers have to build for the realistic worst-case scenarios.
Precisely. So the FEC will almost certainly remain mandatory for 128 GT's operation to guarantee reliability under all specified conditions. But seeing 1010 in a demo is definitely an encouraging sign for the fundamental feasibility of the channel at that speed. It suggests the EQs and other technologies are keeping pace.
Okay, looking even further out now. Maybe crystal ball time. A hypothetical 256 GT's PCIe 8.0. Do we eventually hit a wall with this PM4 and lightweight FEC approach on traditional copper interconnects?
The sources definitely hint at the looming limits. Simply scaling current methods again might become technically infeasible or at least economically impractical on standard copper traces and PCBs. The losses and distortions might just become too extreme.
So what will we have to change?
Reaching something like 256 GTs per lane could require entirely new signaling technologies beyond PM4. Maybe PM8 or something even more complex. Or perhaps we see a broader move towards optical interconnects, even for shorter reaches within computer systems.
Fiber optics inside the box.
Potentially. Or it could demand much more complex, powerful FECs, which might force a serious reevaluation of those critical latency, overhead, and power trade-offs that PCIe has historically prioritized. The balance might have to shift.
Interesting times ahead then. So summing it all up, for PCIe as it stands now and heading into 7.0, forward error correction FEC, it's really no longer just an optional feature or an add-on, it's a fundamental building block.
It's absolutely foundational. It was the critical enabler for making the speed jump with PM4 viable in PCIe 6.0, and it's essential for continuing that speed scaling trend into 7.0 and likely beyond in some form.
And the specific implementation, that carefully layered defense of lightweight, low-latency FEC first, combined with the robust CRC detection second, and the ultimate safety net of LLR third. That whole system is a really clever piece of engineering, tailored specifically to the unique needs, especially the low latency needs of PCIe.
It really is. It's a great example of system-level optimization.
And it's just fascinating how the path to more speed involved accepting a fundamentally messier signal off the wire and then relying on layers of digital smarts to clean it up reliably, rather than just trying to make the raw physical connection perfect.
It's often the necessary evolution when you start pushing hard against fundamental physical limits. You trade analog perfection for digital intelligence.
So here's a final thought for you, the listener, to maybe mull over, taking this idea a bit broader. This layered approach to reliability, where you accept a less than perfect fundamental signal, but then build these layers of correction and detection on top using digital processing, it's definitely not unique to PCIe, right?
Not at all. It's everywhere in high-speed communications.
Think about other high-speed digital systems you encounter every day. maybe the Wi-Fi in your home, the Ethernet cable connecting your computer, maybe even how data is read reliably from a modern high-density SSD or hard drive. How might similar layered strategies, maybe different types of FEC, different detection codes, be at work there? And looking way out, what do you think are the ultimate physical or maybe even economic limits of this whole clean it up in code and hardware approach to achieving reliable communication? Where does that eventually break down?